Hi guys, this is our first video in our new course for AP Human Geo, and we're going to be covering topic 1.1 today, which is Introduction to Maps and Types of Maps. Okay, let's get started. So the first thing we need to know is map scale. So map scales show the relationship between the distance on the map to real life, which is basically saying the map scale is how much the square on your map compares to the square in real life. Map scales vary based on the purpose and the size of the area. And I actually got a question on this next one in the AP exam, so you're really going to want to pay attention to this, is map scales affect the accuracy of the map and how much detail can be put in the map. When you're thinking about this, if you have a large map scale, a very small piece of your actual map compares to a very large piece of the real world, you're not going to be able to fit as much detail in it. Sure, it may be more accurate in representing the area as a whole, because you have a larger view of the whole area, you're encompassing more of it, but there's not as much detail in it. If we go the opposite way, we have a small map scale, where a large part of our map represents a tiniest part of our global scale. We are getting a lot more detail of that area, because now we can fit a lot more, but we're not getting an accurate representation of the area as a whole, since we're focusing a lot more on a tinier topic. So, you need to know what's the pros and cons, the trade-offs to each one, and what's the right scenario to use either one or a combination of the both. Next, there are three ways we can have our map scale demonstrated. Those are in the forms of a ratio, a written scale, and a graphic scale. So onto the right, we have the ratio, which is going to be in the form of number colon number. So our ratio, the number on the left, the 2 in this case, shows the distance on our map. And then the number on the right shows the distance in real life. Usually you're going to see units with this as well, but for now, let's just say 2 inches on our map compares to 1 kilometer of the real world. That's how you can interpret ratios. You need to remember, the left-hand side is for map, middle is colon, you're always going to have that there, that shows there's a relationship, and then on the right-hand side, on the right-hand side is real life. And for ratios, you can also see them in the form of a graphic scale. So a graphic scale is over here on our left, and our graphic scale is a weird combination of black lines and numbers on top. So here's how you're going to read them. For graphic scales, you're actually supposed to put them on the map. Like the graphic scale actually represents the length of the map. So if I have a map, I'm actually going to put the scale on the map, and wherever that 8 mark is, that 8 feet mark, I'm going to trace the black line all the way to 8 feet mark, and that's actually 8 feet on the map. That's how you can interpret your graphic scales. And lastly is a written scale. The written scale is super easy. They spell it out for you. Instead of saying 2 semicolon 1, they're literally going to spell it out for you. Every 2 inches on the map represents 1 kilometer in real life. Okay, let's go over some map types. So there are 3 types of maps. The first is a reference map, and a reference map shows geographical features such as boundaries and landmarks. So if you guys have a map in your classroom, like a world map or map of the US, whichever it is, that's an example of a reference map. We see political boundaries, whether that be state lines or country lines, and we can see landmarks, cities, big areas. That's kind of what a reference map serves. It's like a geographical broad look at an area. On the other hand, we have thematic maps, and thematic maps focus on a specific theme or topic. So if we look at our right-hand side, this is a map of housing in San Diego. And we can tell that the darker it gets, the higher or more expensive it is to buy a house in that area. Is that correct? Yes, it is correct. Sorry. But you're usually going to see thematic maps have to do a lot with color, with darker shades being the extremes and lighters being a lot cooler. So you also need to know that these can do with any theme or topic, as long as it's representing anything as random it can be. It could be potato consumption across the United States. And one example is a map of the CO2 emissions within a city. The scale doesn't matter. What you need to know is on the lookout for thematic maps. They're going to say they're representing a specific topic or theme, like the name is physically going to be potato consumption in the US, and they're usually going to feature color. Okay, our last type of map. Last type of map is topographic maps. And these show elevation, which in case you don't know is the height above sea level. And the closer the lines are together, the steeper the area is. That makes sense. Each line usually represents, obviously you're going to have a scale that tells you how much it is, but normally it's going to be 10 feet higher as each line. So you can imagine if a lot of lines are bunched up together, you're reaching that 10 feet hop a lot quicker. So that's going to be a steeper area. Or if they're farther apart, it's a flatter area. Usually you're going to have to deal with these when they're talking about mountaintops or elevation, and you really just need to keep the line closeness part in mind. You usually don't have to do a lot with reading these. Okay, now before moving into our map projections, what is a map projection? So we need to know a key concept right now, which is that the globe is 3D, right? I'm sorry, flat earthers, it's not happening. And when we have our 3D globe and we're trying to project it on a 2D flat surface, that's literally impossible. A sphere is rounded, right? It's curved. Even if we fold it out, we're still going to be bending it in parts. It can never truly lay flat. So all map projections, all physical maps we have today that are on a straight line have some sort of distortion. And our first one that we really need to know is the Mercator map projection. So in the Mercator map projection, angles and direction are true. This is the perfect map projection when it comes to sailing or seafaring, but our landmass size is distorted. If you see, Antarctica is a lot bigger than you remember, and Greenland is a sign of Africa, which is not true whatsoever. Now, one key example you're going to have to keep in mind with this map is this was commonly used in Europe as a way of dominance. Europe looks a lot bigger in this map projection compared to other map projections, and Europe used this as a way to fuel and scientifically prove that they have dominance over other areas. Our next map projection is the azimuthal, I don't know. But what this is a true depiction of the poles. This is a circular based graph, and we see a true size of the poles compared to the whole Earth. But this is obviously not easily readable, and it's distorted in all ways. Both your direction and your landmass size is distorted aside from the poles. Okay, now let's go over the Robinson. The Robinson is the one you've seen most probably, and this is because it's the least distorted when it comes to direction and size. But the con when it comes to this map projection is everything's distorted. Up until now, everything had at least one part that was true and the others were extremely distorted. This one, everything's distorted by a little bit. Usually you're going to see this now, but you need to know that this is the most accurate representation, but every single thing of it is false. It has no strength. Okay, our last mass projection that you're commonly going to see is the Peters. Obviously, I'm missing out on a few of them, but these are the four I saw as the most important. And what you need to know about the Peters is it's the complete opposite of the Mercator, where it's ignoring all of the latitude, longitude, all the sea level seafaring, and we're instead focusing on true landmass size. So now we're seeing the actual size of each continent. This is the accurate size. We see Africa's a lot bigger than Greenland and Europe now. But the problem is, by putting each continent's actual mass size, we're completely distorting the direction. So that's the con to the Peters projection. Okay, now there are a few more things you need to know, and the first things have to do with distance and direction. Usually these are terms you memorize, if not anything, and I forgot to bold certain words, but I think you guys can live with that. We're firstly going to start off with the absolutes. So the absolute direction is the compass direction between 2 points. This is saying you're northeast, southwest. This is the absolute true direction that's going between these 2 points. Next is the absolute distance, which is the exact measurable distance between 2 points. And usually these points are going to be in the form of coordinates, which have your latitude and longitude. Okay, now the relatives. The relative direction is using relative terms. We're not giving an accurate scientific term like northeast, southwest. We're saying, okay, this point is left of the rock. This point is beneath the table. That's what we're talking about. And the relative distance is perceived distance based on factors. So we're not going to say that traveling to France is a 3,000-mile blah 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 nautical seafaring mile adventure. No, we're gonna say that it's a really long trip because you have to take a flight and it's a 12-hour trip. But that's not an actual true distance, but it's how the distance is relative to us. So this is based off of our factors. Okay, and lastly, we need to know about spatial patterns. So spatial patterns are the arrangement of phenomena across an area. So what this is saying is it's the pattern between a bunch of stuff spread across the map that we're analyzing, or the area, whichever it is. So clustering is when there's a lot of that thing concentrated in one area, and dispersed is the opposite, where everything's spread out and not close to each other. Lastly, we have spatial relationships, which is just a way in which we can see the phenomena connect and how they're organized and how that affects the real world. Okay, thank you so much. We're going to keep updating this series soon. And yeah, just thanks for watching. Leave a comment if you want. And that's all. Goodbye.